So for today's topic, we will be discussing about the genset room layout, genset room foundations, mounting system, ventilation system, exhaust system, noise, multiple genset installations. For the genset room layout, we will be discussing the installation guidelines, the do's and don'ts, and the typical arrangement of the genset room. For the genset room foundations, we will be discussing the recommended foundation pad for the gensets and how to calculate the foundation pad dimensions required. The mounting system, this is an important part of the installation as this will provide adequate support in order to avoid any mechanical failure. The ventilation system, ventilation is the basic principle of ventilation system, and how to calculate the inlet-outlet opening area required will be discussed in detail. The exhaust system, we'll talk about the exhaust system installation, important points to be considered on the exhaust installation, and we'll also calculate the exhaust back pressure. Then we will also have a general overview of the noise. Since noise is also part of the installation considerations, we'll be having a brief overview of it. However, we'll only be discussing just the few points on it and how it can be minimized. And since this is a broad topic, we'll not discuss this in detail since this can be part of another webinar session. Then the multiple genset installation. We'll show you the recommended installation for multiple gensets since this is also following the same principle as the single installation. And for the last part, we'll have the frequently asked questions, and yeah, if you have questions, we'll also be tackling those in case we still have time. The genset room layout. In this screen, you see a typical genset room layout. Genset that is mounted on the foundation pad base frame that is isolated from the genset through flexible mounting, the ventilation system, the exhaust system, as well as the sound attenuators. Each of these components will be discussed in detail as we go along this session. On the next slide is the installation guidelines and important considerations on the proper genset room setup. The installation guidelines, avoid plastic and other unsuitable material for fuel piping and connections, which can corrode or chaff and leak fuel. Keep fuel lines away from hot exhaust pipes, insulate exhaust systems using heat shields or lagging, install a fire extinguishing system in the genset room, make provision for draining the oil sump and fit drip tray underneath. Check entrance is large enough to allow engine alternator to be removed. Provide adequate lighting and power points. And this one is optional, lifting beam in roof for maintenance. Provision for draining engine cooling system. All rotating shafts are adequately guarded for safety purposes. The typical genset room layout. So hot air from the radiator ducted outside the genset room, and it must not allow to recirculate the hot air. Exhaust system to be supported from roofed and flexible bellows fitted used to isolate genset and exhaust system. Hot air outlet ducting, fuel connections, and electrical connections must be flexible type to the engine and alternator. The daily fuel tank is supplied from a bulk tank house remotely from the genset room. The starter batteries are to be kept fully charged during non-running periods by a static charger, which can be incorporated in the control panel. The genset room foundations. Here you can see the foundation pad of the genset, and later on we will be discussing on how it is calculated. So subsoil site, bearing strength capable to support the total genset weight plus the concrete foundation pad. Fixed concrete block, 300 to 450 mm round on all sides of the genset. If the bearing strength of the subsoil is in doubt, advice should be taken from a qualified civil engineer to enable the type and size of concrete foundations to be determined. The fixed concrete block method is the proven effective method in genset installation. After determining the depth of the concrete required for the weight and stability of the running set, the subsoil has to be checked to see if it will carry the total weight of the genset plus the concrete block and withstand the forces involved. So the formula in finding the depth or thickness of the foundation pad is given below. So it is affected by the weight of the generating set divided by the density of concrete times the breadth or the width of concrete block in meters times the length of the concrete block. So on the next slide is a sample. So here we have the JP400. This is a 400 kVA prime genset, which has a total weight of 3,503 kilograms in the length as mentioned here. Using the formula mentioned earlier, we have the depth or the thickness of the foundation pad as approximately 0.3 meters. Therefore, the foundation pad dimension should be 3.6 meters in length, so that is 300 mm longer than the length of the genset base frame. And then the width is 1.42 meters, which is 300 mm longer than the width of the base frame. And the thickness is 0.3 meters, as we've calculated. The mounting. Here you can see an anti-vibration mounting between the base frame and the genset. So on the next slide, we will be discussing the two types of the mounting system. So first, what is the purpose of mounting system? This is used to secure the engine into the installation, provide adequate support in order to avoid mechanical failure, and to allow adequate movement to give engine freedom to move without off-balance forces, provide adequate damping and suppression of the engine vibration. The type of mountings depend upon the type of installation in which the engine is to be used and the final drive arrangement. The engine can be fitted with either solid or flexible mountings. Those are the two types of mountings, depending on the type of foundation or application. If the engine is solidly or flexibly mounted, the exhaust, radiator, and fuel pipe connections must also be flexible. So this is the first type of mounting system, the flexible mounting system. Flexible mounting system enables the supporting base frame to be isolated from the genset. So from the figure here on the left, you can see that the genset assembly is isolated from the base frame. Vibration, the forces generated by the genset being counteracted by allowing the genset itself to move bodily on anti-vibration mounts between the genset and the base frame. That means since the genset will be vibrating, the base frame is isolated from the vibration. And here on this example is a 4-point fixed flexible mounting. We have each here 2 pairs. So one here and then one on the other side, and then one here and one on the other side. So that's the 4-point fix of flexible mountings. Can also be 6-point or 8-point fixes depending on the genset capacity. And another type of mounting system is the solid mounting systems. Solid mountings are used where the movements of a flexibly mounted genset is not acceptable. The genset itself is an integral part of the genset base frame structure. So the genset and the base frame are connected directly together. The genset is integral to the base frame, and then they together are isolated from the floor using these anti-vibration mountings. This allows the genset and base frame to move bodily on anti-vibration mounts between the frame and the floor. So on the next slide, we will be discussing the ventilation. Ventilation is a very crucial part in the installation considerations. The basic principle is to extract hot air from the room and induce air at the outside ambient temperature with minimum recirculation. The objective is to get cool air in the lowest point, push it through the radiator matrix, and out of the building. Radiators must be ducted to the opening. So here's our ducting. And it is unsatisfactory to position the genset so that the radiator is adjacent to the opening in the wall. For the outlet and inlet sizing, the outlet opening should have a free flow area approximately 25% larger than the radiator matrix. Radiator ducting must have a flexible section to isolate vibration and movement. This is particularly important when the set is mounted on the AVMs. So this is the flexible section of the radiator ducting. The inlet, same as the outlet, should have a free flow area of approximately 25% larger than the radiator matrix. On the next slide, we will be calculating the minimum area required for the inlet and outlet. Suppose we have the same genset, JP400, with an engine of 22006AE13 tag 3. The radiator face area from the technical data sheet is 1.238 square meters. So the air inlet and outlet should be 25% larger than the radiator matrix area. So taking the face area of the radiator and adding 25%, we get around 1.55 square meters. So suppose we will install a grill or a louver in front of the radiator ducting, we'll have to consider this restriction on the grill. So suppose the free area is 80%, we'll divide the area of the outlet and the inlet by the 80%, so 1.55 square meters divided by 0.8. Therefore, the minimum area of the inlet and outlet should be 1.934 square meters. So 2 square meters of inlet and outlet should be acceptable. One important thing to consider on the ventilation system is the duct resistance. So the radiator duct allowance must not be exceeded. Exceeding the duct allowance can cause the fan to run in a stalled condition. Running a fan in stall will lead to fan failure. Airflow must be measured at the radiator outlet matrix to determine the actual flow. Measured flow must be at least the design minimum flow. If minimum design airflow is achieved with minimal margin at core phase, it is unlikely that sufficient airflow will be available once the front attenuation and the louvers are placed. There are cases where the radiator ducting will be installed against prevailing wind. So the radiator fan of the genset is a pusher type. If the prevailing wind is blowing into the opening, additional resistance will be put on the fan with a resulting reduction in cooling airflow. If the above condition is not possible, other methods should be considered. That is, ducting the radiator outside at 90 degrees to the cooling airflow and adding a deflector panel in front of the radiator. So using these methods, minimize the back pressure on the fan. The next part, we will be discussing the exhaust system. Here in the figure, you can see we have the generator room layout with the exhaust system. We have the flexible bellow, the exhaust pipe from flexible bellow to the silencer. And then from silencer, we have an exhaust pipe to take the hot air outside. In some cases, the exhaust piping is vertical. So in that kind of installation, a flap should be installed at the top of the exhaust pipe to avoid any rain ingress or routing the exhaust pipe 90 degrees horizontal so as to avoid any air ingress. It is also important to note that the exhaust piping has to be unequal in spaces. This is to prevent buildup of resonant pipe vibrations. Long piping runs should be supported at unequal distances. So this is a recommended exhaust pipe routing instead of the equally spaced ones. Part of the exhaust system is the discussion on the exhaust back pressure. It is important to note that the following are the effects of excessive exhaust back pressure. Too high a back pressure leads to poor fuel economy. So fuel consumption increases by approximately 0.5% for each 3.3 kilopascal above maximum level. High combustion temperature, so that's 2.5% increase in exhaust gas temperature for each 3.3 kPa above maximum level. These conditions produce overheating and excessive smoke from the installation, and these can reduce the lives of the valve heads and the valve seats. Because of the above, the limit on the back pressure must not be exceeded. The exhaust pipe internal bore will have to be increased or pipe run length reduced to minimize back pressure. The major design factors that may cause high back pressure are the following. Exhaust pipe diameter is too small. Exhaust pipe too long. Too many sharp bends in the exhaust system. Exhaust silencer restriction too high. So in case the exhaust back pressure is above the limit, the following factors must be adjusted. For example, we can increase the pipe diameter or minimize the exhaust pipe length. The formula we used in calculating the exhaust back pressure is here. It is affected by the total length of the pipe, directly proportional to the length of the pipe, by the density of gas and the gas flow. And it is inversely proportional to the diameter. The equivalent length of straight pipe, so let's say for example, we have bends, we have elbows. So we have to determine the equivalent straight pipe in order for us to calculate the exhaust back pressure. So we can use the following equations in determining the straight pipe length. For the standard elbow, we have here. For the long elbow, we have this 45-degree elbow and the square elbow. So take for example, the same JP400 with 3.5 meter straight pipe, one 90-degree bend, one 500 mm flexible bellow, and a residential silencer with 4 kilopascal of pressure drop. From the engine data sheet, we can take the exhaust gas flow and the value of the exhaust gas temperature, and also the limit of the maximum back pressure allowed. So first, we have to calculate the equivalent straight pipe length. So we've already said that the straight pipe is 3.5 meters. Then we have the 90-degree elbow. Calculating the equivalent straight pipe, L is equal to 33D over X. So the internal diameter of the exhaust pipe is 6 inches, equivalent to 152.4 mm. So 33 times 152.4 divided by 1,000, we have 5.03 meters of equivalent straight pipe for the 90-degree elbow. And the flexible bellow, that is 500 mm in length, should be multiplied by 2 to get the equivalent straight pipe. So we have 1 meter. In total, we have 9.53 meters of equivalent straight pipe. So that is from the route that we've taken. Calculating the exhaust back pressure, so plugging those data in, we have the 3.6 times 10 to the raised to the 6th power times the total length times the S, which is calculated using this formula, and then multiplied by the exhaust gas flow from the engine datasheet, all divided by the diameter of the pipe, plus the back pressure of the silencer. Back pressure is equal to 4.85 kilopascal, which is less than the maximum allowed back pressure on the engine. That means our exhaust system piping is acceptable. And in case this is greater than 10 kilopascal, then we can make some adjustments here, like lessening the pipe route. Instead of 3.5, we can go lower. And instead of 152.4 mm diameter of exhaust pipe, we can increase this. So we can make necessary adjustments to ensure that the exhaust back pressure is within the limit allowed on the engine, mentioned in the engine datasheet. The next part will be discussing on the noise. But as mentioned earlier, noise is a broad topic and it can be part of another webinar session. So we will not be discussing that in detail. We'll only be discussing the source of noise on the engine and how it can be minimized. Noise is generally defined as unwanted sound. Sound itself consists of small pressure variations in the air, the source of which may be either a vibrating structure or a pulsating gas flow. Should additional noise reduction be required, this can be achieved by acoustic treatment. Installation of baffles on the inlet and the outlet sides of the genset will help lessen the noise, taking into consideration that the pressure drop limit specified on the datasheet must not be exceeded. And acoustic treatment design should be consulted with acoustics specialists. The next part, we have the multiple genset installation. Multiple genset installation is much like the single genset installation. Generally, multiple genset installation follow the same principle as a single unit installation. It is important to note that exhaust gas from multiple gensets must not be combined into a common exhaust system, as this can be very dangerous and could cause engine damage. So the manner of installation of the multiple gensets should be side by side. The hot air from the Genset 1 should not go to the Genset 2 and to the Genset 3. So it is recommended that during multiple installation, the gensets must be installed side by side. Same side of the inlet and same side of the outlet. And now let's move on to the frequently asked questions on the generator installation. We have here, what is the recommended clearance around the genset? So, take for example, a single genset installation. It is recommended to have 1 meter clearance from the genset to the wall to accommodate for the maintenance. For multiple genset installations, what is the distance between each genset? So each genset should have 2 meters of distance from each other. So from earlier here, this genset should have 2 meters of gap from this one so as to facilitate for the maintenance. This genset should also have 2 meters of distance from the other genset, and from the wall, it should have 1 meter of distance. What should be done if the exhaust back pressure exceeds the engine limit? So if the exhaust back pressure exceeds the maximum allowed exhaust back pressure mentioned in the data sheet, we can reduce the pipe length run, we can increase the pipe diameter, and we can also reduce the number of bends. And what is the recommended radiator duct length from radiator to the louver? So the recommended radiator duct length from radiator to the louver is 1 meter. What is the effect of high exhaust back pressure on the genset performance? As a rule of thumb, the loss of power or the effect of the high exhaust back pressure on the genset performance is approximately 0.5% decrease for each 3.3 kilopascal above maximum level. So that's it for our today's session. We can go ahead on the questions posted by you guys. Is flexible mounting same as spring type mountings? Well, actually, spring type mounting is a type of isolator. Spring type is a type of isolator, not type of a mounting system. Flexible mounting means that the genset is isolated from the base frame, as we've seen earlier from the slides. Instead of the genset being an integral part of the base frame, the genset is isolated from the base frame, and the base frame is directly connected on the floor or the foundation pad. Next question. What's the effect of using a welded pump rather than elbows in exhaust piping? Emmanuel, I don't know what you mean by welded pump. Rather than elbows, because typically the exhaust system is installed. So from the engine, we'll have the exhaust pipe, the bellow, and then exhaust pipe. Then we'll have the silencer, and from the silencer to outside, it's just straight pipe. So I don't think there should be a pump on the exhaust piping system. Welded pipes, okay, welded pipes. When you say welded pipe, so that means the exhaust system, the exhaust pipe are welded together. So what's the effect of using welded pipes rather than elbows in the exhaust system? So if the welded pipe is just a straight pipe, then there won't be much effect on the exhaust back pressure, because elbows have greater effect on the exhaust back pressure. Yeah. Next question, please. What is the maximum quantity of 90-degree elbows and 45-degree elbows can be used for installation of exhaust piping? So the number of 90-degree bends and the 45-degree bends depend on the maximum allowable exhaust back pressure. Say, for example, our JP400 earlier, it has a limit of 10 kPa, kilopascal. As long as you're not exceeding that 10 kilopascal, you can have as much bends as you need. So using the formula that I've shown earlier, you can calculate the exhaust back pressure. So it is dependent on the allowed back pressure. So there's no fixed number of 90-degree bends and fixed number of 45-degree bends. So we'll always have to calculate, and we'll always have to be less than the maximum allowed back pressure. So if you have any installation design that has this much 90 degrees and 45-degree elbows, you can share it with us, and then we can help you in calculating what is the maximum 90-degree and 45-degree elbows that can be used on that particular genset. Of course, we'll have to determine, or we'll have to know the details of the engine as well. Next question, please. What should be minimum distance from the radiator to the louver for ducting? So earlier from the frequently asked questions, it is there. The minimum distance from the radiator to the louver for ducting is 1 meter. So that's the ideal distance. Next, please. Is the turbocharged gensets have the same exhaust back pressure and calculation? Yeah, that that formula is applicable to the turbocharged gensets, because this is depending on the limit mentioned on the engine data sheet. So as long as we are not exceeding that limit, whatever is the engine type, may it be naturally aspirated or turbocharged, we can use the same calculation, same formula. And the exhaust back pressure, the limit, the maximum allowable exhaust back pressure will always be found on the engine technical data sheet. So it varies from one engine to another. So it always have to be depending on the mentioned exhaust back pressure. Next, please. Okay, so that's it. If you still have further questions, you can drop those at solutions@golf@jubileeplus.com.